All right, today we're going to be talking in IA201 about modern drives. Motor drives are the growing segment of motor control. That is the biggest growing segment. And the reason why is because they are very cost effective. Not only cost effective in terms of just buying them outright, but the fact that they add a lot of features to the motor and let you run that motor less expensively. So they are a vast improvement in the basic use of motors in many manufacturing facilities. Not to say that they've taken over the market, because we still have a lot of equipment out there, old school equipment with the old school drives. And not only that, we've got a lot of old school engineers who are stuck in their ways and still like to use standard motor starters. And that's probably not going to change for the next 10 or 20 years. But drives are slowly advancing and taking over the market of running motors, especially on the lower end, the smaller motor sizes. So we're on page 555, and let's talk about chapter 26. There's a really good introduction to chapter 26. I usually don't talk about the introductions so much, but this is a very important fact here. Improvements are continuously being made in the performance, operating speed, and applications of control circuits, right? Functions once performed mechanically are now performed electronically. And that is a really important statement, because we were replacing the magnetic motor starters more and more and more. So on this page, we learn about what a motor drive is. They give you the basic definition of it. And the definition they use is, they say it's an electronic unit designed to control the motor speed for AC or DC motors. And it's often used to control the motor direction. So I get reversing built into it. I can control the speed into it, and I can control the acceleration. And most importantly, that's not mentioned here, is I can control the torque. I can have very precise torque control as well for a motor drive. So that's a very, very important fact. And the book also mentions that the AC are the most common because they can vary the speed of a three-phase motor. And three-phase motors don't require nearly the maintenance of any kind of single-phase motor. So, and also I mentioned here, very important, that they don't mention in the book at all, is it's cheap. It's becoming cheaper and cheaper and cheaper to buy these drives. And typically they are now at the same price or less the same price than a reversing motor starter. And in some cases, they're cheaper than just a plain old motor starter. In this section, we talk a little bit about how regular magnetic motor starters work. And they actually give you a falsehood in here. They say the cost of using a magnetic motor starter or motor drive is about the same for any horsepower rating. That's not quite true. Standard motor starters create a huge, let me zoom out here a little bit. Standard motor starters create an extra spike of energy when they're being fired up. And that extra spike of energy, depending on how your plant is operating, often creates a problem in terms of your power rates. By reducing that extra spike of current requirements, you actually can start to have an effect on reducing your overall energy costs. So even though technically this is true, like once you get up and running, on average, it uses the same power, from a overall plant power management standpoint, this is not entirely true. There is a reduction in cost, slight, purely in your power cost. And they talk a little bit more about how we'd use a magnetic starter. They give you examples of different kind of starter circuits. Which is just a repetition, in my opinion, previous. So then on page 558, we start getting into various motor drive control circuits. And they give you the example of a couple different control circuits. And so the first example is 26-3, where they show you a typical motor drive. And they don't quite show this to you in the picture, but you wire in your three-phase power into the top of it just using 3 big terminals. And then you wire the 3 legs that go to your three-phase motor, T1, T2, and T3 out the bottom. And then there's a set of additional terminals which would optionally give you the ability to control that motor either from a faceplate. They don't actually show you the faceplate on here, but often you can control that motor directly from the faceplate, like I showed you in Automation Direct, or you can wire up using a small terminal strip at the bottom here for your control wiring. So you might wire up this little circuit to an on-off or a hand-off auto configuration for some sort of automatic level control. And so that's an example of how you would wire this VFD up using their little control terminal switch. And their control terminal switch has little positions on it to give you like a 10-volt DC signal, and then if it receives that signal back to the start contact, that means it wants you to run that motor. And you can put a reverse in there. If you want to have a forward reverse, you can run that motor reverse. You can jog that motor, or you just want to run it while that's on and then release it. You know, you have all these options built into your VFD. And this is a very simple one. So the book takes you through some of, kind of in detail how that really works. The book also mentions one of the key advantages, which is speed control. I can actually, from the faceplate, have a little knob where I adjust the speed, or a little up-down arrow, or I can hook it up to an external source for speed control. In this case, I can hook it up to a potentiometer, which is basically just a little knob that I can adjust. Do I have one of those here? No, not handy. That way I control the speed from potentiometer, or I can hook it up to a PLC and have the PLC output a signal to determine how fast I want that motor to run. So the option of these multiple capability is way beyond a simple magnetic starter, way beyond. And then the book takes you through on page 560 what the typical configurations might be for some of these drives. This particular drive they're showing has got a bunch of dip switches to control how you're setting up that drive. A lot of drives have programming where they mention here on, started into programming on 26.2. A lot of them have programming as well. But this particular drive they're showing is an ABB drive with a bunch of little dials you can set to set up the frequency, the max horsepower, and other configurations. And they also have dip switches in here where you can set various configurations for how you want to run that drive. This is a lot more complex than many drives we get nowadays, where all of these things are set in the programming, and very few are set through dip switches or little switches like that, little potentiometers like that. So most drives that I've run into, especially in the smaller horsepower range, have all this configuration information instead of dip switches set up to be software. So let's talk about, on page 561, we're going to get into programming motor drives. Programming these motor drives is kind of a pain in the rear end. You once you learn how to set up one or two, then they all start to follow the same pattern. But basically, you program by hitting push buttons on the faceplate. The push button faceplate we're seeing here looks like an Allen Bradley drive, the 50 that we've got in the classroom. And basically by using the select key, the escape key to back out, the select key to select it, and then the up and down arrows, I can cycle through a variety of configuration screens, programming screens, and basically display screens so I can see what's going on with that motor. In our motors control, in our power transmission class, we had to cycle through some display screens to look at various things going on with our motor. And we had some really advanced stuff for, that you just wouldn't have found 10 years ago. For instance, we could check and see exactly how much current that motor was using. We could see how many amps. We could see how much power. We could check the voltage real time, see what the voltage is doing. And of course we had speed control. So we had a lot of things that we could just display by cycling through the display menu. Now, most of you guys are relatively young, so you've grown up with a lot of devices that are programmed like this or in similar ways. So hopefully you guys are all predisposed to understand this a little bit more intuitively. My generation, though, and older, we've had some challenges in figuring out how to program these, just purely based on the fact this is a lot of menus packed in accessing just a few push buttons. So if you've ever worked a controller and done some setup and configuration for your gaming system, you almost have some of the same sort of approach here. Yeah, and I think we had to walk 10 miles in the snow uphill every day to and from school. So that's my
While fighting
official.
off dinosaurs too.
What's that?
While fighting off dinosaurs too.
Exactly. Had to get out my club to whack the dinosaurs. Pesky little things. But the bottom line is this is sort of a learned skill that anybody can learn. And the first few times it was a little bit of a struggle for me, but then you get used to it. We're not actually going to be doing any programming here in our labs, though I can certainly, when we get into our labs for the last couple of days, we can set one up as sort of an option and see how easy it is to wire up and use compared to any other kind of motor contactor circuit. But here in the book, they actually take you through some traditional programming for, I believe this is the Allen Bradley one. This looks like the exact tables we get in Allen Bradley. So you have various parameters you can display. They just show you a small kind of subset. Output frequency, how fast I'm running that motor. Command frequency, output current, output voltage. And there's more. You have plenty of different other displays you can set up to look at for that particular motor, depending, of course, on the drive. Some drives have less, some drives have more. You've got this parameters you can set up for display. You also have some programming where you're setting up the basic, the setups of the basic wiring. How are you wired into that? Or are you using any of the wiring options, or are you just using the keypad only? So the default for, say, parameter 36 is 0 keypad. So that way we know that at all times the keypad is going to be the one controlling the speed and start and stop. Or I can wire it in using a couple different wiring schemes, so I can have different settings here. I also set the min-max frequency for my motor. I also set the current for overload. This is my built-in overload protection, so I make sure I don't send too much current down to my motor and cook my motor. I can set up the maximum motor frequency and the maximum motor volts. And these all come from the faceplate of the motor, so I can set up this stuff and run the VFD for any motor I select. Now, the downside is if you have somebody in there messing around with parameters, they can cause a lot of very expensive damage, right? Whereas in an old school motor starter, it's got the heaters that its designer installed with it, and you can't mess with those heaters very easily unless you physically unscrew them and go find a overcurrent heater. I guess you could do that. But here, anybody with a programming access can get in there and mess with parameters. Advanced programming parameters, there's a lot. We can have ramp time, we can do jog capability, we can have deceleration, acceleration. We've got a lot of different advanced parameters, pages of them in many VFDs. And the book just goes through typical examples for all this stuff. I think I've got a video I put out there on drives. I'm going to encourage you to watch that video. It does a really good job of not just talking about this stuff, but showing this stuff for this class. I think that's great. So now we're on page 565, section 26-3. We're going to dive into DC motor drives. Now, do you guys remember what I said about DC motor drives? Well, why are they becoming less common? And it's usually to do with money, because DC motors are becoming more expensive compared to AC motors. DC motors, like a permanent magnet DC motor, you have to replace the brushes. You have potential more problems things that could break, like the commutator. And so that DC motor that used to be very cost effective, say 15 years ago, is no longer your best option because the VFDs, these AC drives, have become so cheap. But they're still out there. We still have a bunch of DC drives. Very small DC drives, are still plenty of them out there. They're still in common usage, and they're good to know. In fact, in our Motors and Controls 2 class, we do a couple different DC drives. So they talk about a couple different methods of DC drives. And one thing that's very key with DC drives is you have the capability of doing regenerative braking. And as a matter of fact, if you're talking about, say, a Tesla, if you put your foot on the brake in a Tesla, for that first length of travel, you're actually converting the momentum of your vehicle into a big generator. You're using those motors as generators. So that helps you recharge your battery. So that is a huge advantage of DC drives. I don't think this book even talks about electric vehicles. It's too staid and old-fashioned. But yeah, electric vehicles are one of the last and probably most important area we're going to find some sort of DC drive. And one reason for that is because you can recharge your batteries somewhat. There's some energy loss from friction, but you can recharge your batteries somewhat every time you put your foot on the brake in a DC drive situation, if you have regenerative braking. But we also can use regenerative braking as a technique to slow the motor down, and that's built into DC drives. For some reason, the book talks about the power source for DC drive, and it talks about the circuits you would use to create a DC voltage using rectifiers, and 2 rectifiers to create a ripple, 4 rectifiers to create full wave bridge. Then you could have some smoothing built into it. Then you can have a fancier system here. Full wave smoothed outputs typical for DC drives. But what they don't tell you is this is often also included in AC drives, because AC drives, they take DC power first. They convert your 3-phase stuff into DC power, and then they use that DC power as the source for sending out high frequency, using high frequency switching down to your motor. So this is also the same kind of input you have for an AC drive. It's in the inside though. You don't physically see any of these things inside of a typical AC or DC drive. This is all happening inside. So key terms to think about with DC drive is, of course, the braking bit, dynamic braking, as well as regenerative braking. Both of them are a key aspect to running a DC drive. And that kind of remains one of the areas where DC drives do have advantages over AC, is the capability for braking. All right, so actually here in 26.4, they dive into AC motor drives and how they convert the power from three-phase power to a DC circuit. They show you this whole DC circuit being created using this bridge rectifier configuration. And then once you've got your DC circuit, you've got the ability to switch it on and off using these bipolar junctions transistors. They're heavy duty power transistors that you can turn on and off using control logic. This little bitty computer is built into your drives and then switches on and off the power that goes to your motor. And so the book talks about how that whole conversion process works and creates a DC bus. And then that DC bus is used with some filtering capacitors to give you a better circuit, and talks about the relationship between voltage and frequency in the output. So capacitors, we talk about capacitors on page 572, and we use them in the circuit. The inverter is the last portion of the DC. So it's converted with an inverter into an AC, high frequency or low frequency, any frequency you want, output that goes down to the motor. And that's mentioned on the bottom of page 572. So the key fact about VFDs, any sort of high frequency output drives, is the voltage applied to the stator, that's the outside portion of the AC motor, must be decreased by the same amount as the frequency. Motor heats excessively and damage occurs to the windings if the voltage is not reduced when the frequency is reduced. Right? So when you reduce your frequency, you're getting more energy per cycle, right? So you can't have too much energy per cycle. That energy, that watts, goes into your motor, and you have to reduce the voltage if you reduce the frequency. Otherwise, you get too much power in your motor, too many amps rating, and that amperage will then cause your motor to cook. If you have too many amps in your motor, that's how you cook your motor. So that's a little fun fact, important. The book also talks on page 574 about how a VFD controls torque. Torque is absolutely a critical part about VFDs. It really makes them a huge advantage over regular motor starters. When a regular motor starter fires up, right, you generally have a torque speed curve, and you really don't have high torque necessarily at your starting speeds. So you're consuming a whole lot of extra amperage to keep that motor, start that motor turning around. And so using a VFD, we have the ability to create a high torque, low speed environment. So that's a real advantage for a VFD. The book talks about carrier frequencies, and that's interesting stuff. Not really critical from a technician standpoint. And it does, in the higher quality ones, tend to have a higher potential carrier frequency. And the carrier frequency needs to be substantially faster than the fundamental frequency that you're sending out to your motor. As you can see, in your carrier frequency, you just decide what percentage of that tiny fraction of time you're going to be powering up that particular phase to the positive or to the negative. And that's a concept that's useful, but not really much useful from anybody but somebody who's designing these things. But that's one reason why you do have higher dollar VFDs. They can create a slightly better sine wave if they have a higher frequency carrier frequency. And here's the fact that you should remember. The only thing that's really important about carrier frequency for you guys, higher carrier frequencies are better than lower carrier frequencies to a certain extent, right? So that's as far as they go as supporting the concept of high carrier frequency. Another important term, but not really critical from understanding how these things work, pulse width modulation, PWM. It's a method of controlling the voltage using pulse width. So how wide is the pulse of energy? Now, stopping methods, they can have a variety of methods of slowing down and stopping that motor. And you have soft stop, you've got ramp stop, you've got coast stop. These are all different stopping methods. The most typical is ramp stop, where you want to ramp that motor speed down. We can, on some systems, have DC brakes where you actually inject a through one of your stator coils a DC voltage, which has the effect of braking that AC motor, which is really cool. But guess what? It might generate a lot of extra energy for your VFD. So if you try to make a DC brake, and this is on the top of page 579, it could cook your VFDs. So sometimes VFDs, when you do this DC braking, require that you put in a resistor. And that depends on the model of the VFD. Sometimes you have to go buy a resistor. So fair warning for all technicians out there or any engineers, if you're designing a system with braking, make sure you read all the fine print and get all the parts you need to make it work properly. Plus, if you have too small a resistor, guess what? You're just going to melt it and it won't work very well. The next section starts on the bottom of page 579. We talk about overloads. Instead of having heaters, little things that heat up and pop open and whatever, you've got electronic overloads, which are typical for motor starters. Nowadays, many of them have electronic overloads. They know when there's too much current being sent down to the motor, and you can program them. Some of the older drives, they're adjustable like this, just like you have on a typical magnetic motor starter. But most of the newer drives have them set up as parameters, in my experience. So you have to set them up ahead of time and program them. And it talks about how you would set them up, usually based on nameplate of the motor. They talk about the AC motor drive load test. how you could test whether it works right, and that's useful information. And they give you a little section on troubleshooting. The section on troubleshooting, from my opinion, isn't a whole lot different than troubleshooting any magnetic motor starter. However, now you have the option of pulling out an oscilloscope and analyzing the details of that output. So you could spend a lot more money and time to figure out what's wrong with an AC motor drive. So I'm not going to dive into the troubleshooting section, but please read through it. It's got some really useful stuff, and follow the procedure. Once again, this is one of the more useful bits of the book.